All right. Okay. Hi, everyone. Welcome to the last session of 3 talks for SNUFA this year. We have Charlotte Frenkel from TU Delft, who is basically in her talk title trying to hit every single topic that we're interested in SNUFA. So we've got artificial neural networks, we've got biological neural networks, and we've got neuromorphic all in one talk. So yeah, so this is going to be pretty cool and perfect for this community, I think. Charlotte, please. Go ahead.
Thank you, Ben, for this great introduction. So indeed, in this talk, I'm going to talk about how to merge insights from artificial and biological neural networks for neuromorphic edge intelligence. And more specifically, we are going to cover 3 main questions. So the first one is, how should we exploit and make the best of the synergies between neuroscience and AI? And more specifically, what is the right perspective and the right starting point to make the best of these synergies? The second point is, why should we bother at all with neuroscience, actually? And the third point is, how can we morph these questions into interesting engineering solutions? So we'll go all the way from science to engineering. So with this planning and this menu, let's start with the first point, how to exploit the synergies between neuroscience and AI, and more specifically, let's look at the perspective. So we have this bidirectional interaction between neuroscience and AI. So there are really 2 ways to go. The first one is from neuroscience to AI. And basically, the goal is to identify what are the brain computational primitives, what are the key ones, and how to scale them to AI-oriented workloads. So this is really an approach that is grounded on science. And for example, what we have seen yesterday with the dendritic approach, it's very much aligned with this way to go from neuroscience to and how to scale it to AI. But actually, there's also another way to go, which is to start from existing AI algorithms, so for example, backprop, and how to align it with neuroscience inside. So this is now really about engineering. So you are going to engineer your algorithm in order to align with neuroscience. And this is, for example, the whole field of bio-inspired backprop. But the problem is that it's still quite unclear what is the right perspective on to what is the best way to go. Should we go for science or the engineering part? And I think we miss a perspective, and the standpoint that we'll take in this talk is actually that hardware forms a very interesting middle ground to shed some light as to how should we make the best of neuroscience and AI. And so let's look at the synergies. From AI to hardware, we have an obvious synergy, that is that AI without hardware isn't sustainable. So most of you are probably familiar with this kind of graph showing how the training compute requirements scale over time for popular AI workloads. So we were used to a scaling of about 15 times more compute every 2 years, but now even with the transformer models now, it's even going about 700 times every 2 years, which is completely unsustainable. Because when you look in Moore's law, you gain from technology progress only about a factor of 2 every 2 years. So the only way to scale is completely unsustainable. It is about scaling the size of the GPU server farms. And if we do not take hardware into account and make hardware more specific to support the scaling, at some point, the scaling will have to stop due to economic constraints. So that's one way to go. This is the obvious synergy between AI and hardware. And actually, there are also synergies between neuroscience and hardware. And these are less obvious, so they deserve a second point in this presentation. Why should we bother at all with neuroscience? And let's uncover what are the synergies between neuroscience and hardware. So I told you there are 2 ways to go. So let's start from the first way to go, going from neuroscience to hardware. So here we'll focus on one specific case, which is synaptic plasticity, and this will take neuroscience as a starting point. So when we talk about synaptic plasticity, usually the main starting point is STDP, or spike timing dependent plasticity. Whether it's the right starting point is another question, but for the sake of this talk, for now, let's focus on STDP. So STDP is just postulating that every time you have a presynaptic spike before a postsynaptic spike, you have that the relationship is causal and you will potentiate your synapse. If it's anti-causal, so the postsynaptic spike comes before the presynaptic spike, then you will have to depress your weight. So this is about the synapse that is in between these 2 neurons, and this is a local learning rule. There's actually another way to formulate a quite similar learning rule, which is spike-dependent synaptic plasticity, or SDSP for short, proposed in this paper. So the figure itself is not very important. What you have to remember is that now the mechanism is that for every presynaptic spike, you look into the state of the postsynaptic neuron at the time of the presynaptic spike. So this is also a local learning rule. And so what we have is that we have slightly different mechanisms, but both of these learning rules typically have the same learning performance. And so how should we choose whether we go for one or the other? And so here comes my point. Let's switch to hardware and investigate a little bit what it looks like on this side. So some of you might not be familiar with hardware. That's not a big deal. On the left, you have a digital implementation of an STDP synapse. On the right, you have a digital implementation of an SDSP synapse. And what you have to see is that for a CDP synapse, you have to compute inside every single synapse a time window in order to remember what is the spike time difference between the pre and the postsynaptic neuron. And you have to do that inside every single synapse. And there are 100 to 10,000 synapses per neuron, so this is really expensive to do. On the other hand, you have the SDSP synapse, and you do not have to do such computations. You just need to look up the state of the postsynaptic neuron every time you get a presynaptic spike. So that leads to huge savings. And now that we come back to neuroscience, thanks to hardware, we can shed some light into this question. The fact that both learning rules are local is not the end of the story. They are both local in space, but only SDSP is local in time. You do not need to compute the time difference there, and that leads to huge silicon savings. And that can also hint to more bioplausible mechanisms. For example, if you look into this paper, you can see that voltage-based learning rules are more bioplausible than learning rules that are purely based on the timing of spikes. So here is an example of how going back and forth between neuroscience and hardware can guide as to what is more bioplausible and more hardware efficient. So let's go the other way around. Now let's start from the AI algorithms and move with bioplausibility now as the end goal. So if we talk now about neural network training, we have that the most common starting point is backprop, because it's just a standard workhorse of deep learning. So let's see how to align backprop with more bioplausible learning algorithms. You have two big problems with backprop. One is the weight transport. You need to access the transpose of the weight matrix during the backward path. And that is not bioplausible because that implies that synapses would be bidirectional. And this is really not plausible. The other problem is that, for example, before updating this weight matrix, you need to do the full forward path and then the full backward path before you can update it. So this is known as update locking. You can really not do anything about this weight matrix before you do full forward and then the full backward path. And this is not bioplausible because that implies two phases in learning, which the brain doesn't do. All the synapses learn in parallel and in real time in the brain. So let's work on solving these two issues. So a quite famous algorithm is feedback alignment, and it just replaces the transpose of the weight matrix in the backward path by a fixed random connectivity matrix. And the algorithm is, this learning algorithm is still able to learn useful representations. It actually figures out how to propagate useful error information through this fixed random connectivity matrix. There's another variant that is called direct feedback alignment, and now you just use fixed random projections of the final error in order to, as a surrogate for the layer-wise gradients. And what you can see is that both of these algorithms release the weight transport, but they do not release update locking. You still have to do this full forward pass followed by full backward pass. And same here, you have to do the full forward pass. And although here you have that the latency, the backward pass, you have this shortcut path here, so it's shortened, but it's still there. And so we got an idea. We thought about, okay, what if we just use the sign of the error here instead of the error itself? And then you have a very nice property for classification problems, is that this allows to release update locking. Why? Because for classification problems, the target signal here is just in one hot encoding of the classification label. That is 1 for the correct class and 0 for the incorrect class. So here's the definition of the error, that is the target vector minus the network output, which is usually selected as, for example, a softmax, which is strictly bounded between 0 and 1. And so if you compute the error, you have 1 minus something that is strictly bounded between 0 and 1, so it's always positive for the correct class. And similarly, it is always negative for the incorrect classes. So what that means is that the sign of the error is known in advance for classification problems. And if it is known in advance, that means that you do not need to do the full forward pass before you get this information. So you can use this property to release update locking, and this leads to our direct random target projection algorithm, which just uses fixed random connectivity projections of this target vector. So what you can see is that actually, interestingly now, if you look into neuroscience, you can see that the RTP can align with output-independent target signals in the dendritic path, dendritic into instructive pathways of cortical intermediate layer neurons. What that means is that the RTP can align with some of the mechanisms that are used in the brain. I'm not saying that the RTP is the mechanism that the brain uses, but it aligns with some of these mechanisms. But even more interestingly, because now we made backprop more bioplausible, we also made it more hardware efficient, because if you go from here to there, you really released computational and memory costs. And for example, we demonstrated this with a chip that embeds the DRTP algorithm. And we demonstrated that there's only a 15% overhead in power in an area compared to the inference-only network. So we really demonstrate that this is a cheap learning algorithm that you can implement on chip. So what I would like to convey, in case I lost you for this slide, is that hardware efficiency and bio-plausibility are often two sides of the same coin. We have seen first with a more science-driven approach that designing efficient hardware hints toward bio-plausible mechanisms. Why? For the more AI-driven approach, we have seen that bringing AI closer to neuroscience actually leads to more hardware efficiency. So these two sides of the same coin is actually this nice synergy that was hinted before as a question mark. This is a natural synergy between neuroscience and hardware. But we still haven't answered what is the right starting point. So for this perspective, we have seen that hardware brings a nice light into these synergies, but what is the right starting point? Should we go from science or should we go for engineering? And so we have seen just before in this presentation that, okay, we have followed a science approach that is really what we call bottom-up. So it's about analysis by synthesis. It's about understanding by building. For example, this is about this STDP synapse that we try to replicate in silicon, and then we can better understand and infer how the brain is processing. But the problem is that, and I'm coming back to a remark that I have made in the beginning of my talk as to whether STDP is the right starting point. It is very difficult to scale efficiently such bio-plausible learning rules to a real-world problem. You can, for example, scale STDP to endless, but beyond that is extremely difficult. So now comes the engineering approach. Now it is called a top-down engineering-driven approach. So what is nice here is that you really start from the working solution to real-world problems because you start from backprop. But the question is that which salt and pepper from neuroscience should you take in order to lead to more efficient learning algorithms that can outperform conventional approaches? Because this is really the question that you would like to answer with bio-inspired AI algorithms. And so the second standpoint that we'll take in this talk is that actually to achieve what we call neuromorphic intelligence, you should use this top-down engineering-driven approach, and it should be fed by insight from science and a more bottom-up approach. So let's see now, by using this approach, how we can morph these questions into interesting engineering solutions. So because we are now transitioning to engineering, we need a use case. And so the question that we'll focus on is on-chip learning. And so let's see why we need on-chip learning. You have that for every inference device. So for example, your smartwatch that you want to do some keyword spotting. You provide some data, and you receive some decision, and the performance is going to be within the specifications only if the input data follows the distribution that was used during training. As soon as you get out of distribution data, you have that the performance will drop. And so where does this out of distribution data where is it coming from? It can come from different users and environments, features that you haven't predicted ahead, and even from task requirements that need to evolve over time. So for example, you would like to program your device to learn a new keyword. How do you do that? And so what is worse is that, okay, typically decision can be within the performance boundaries at the beginning of the lifetime of the device, but as time evolves, you have that these features can evolve over time, and you will get more out of distribution data over time. So how to solve this problem? You can always use more training data before deployment to cover more cases. But the problem is that this has a cost to gather and curate such massive amounts of data, and that's never a robustness and flexibility guarantee in the long term. The second thing that we can do is typically what is done actually, is a data exchange with the cloud. The problem is that you have to consume energy from your battery to do so. So if you have a very tiny device, battery-operated device, this typically can be very expensive. And also you might need to leak user-specific data to the cloud, and therefore this comes with a privacy issue. So that is why it is interesting to investigate on-chip training, and we'll make it bio-inspired and end-to-end. By end-to-end, I mean there is no external memory, because in hardware design, accessing external memory is extremely expensive power-wise. So we would like everything to happen on-chip. So okay, so far so good, but the problem is that we still haven't identified our real use case, is that because achieving on-chip training for such temporal data, so for example, video or speech, is still an open problem. And why is it an open problem? Is that for temporal data, the workhorse of deep learning is backpropagation through time. And the problem here is that let's suppose you have temporal data lasting 1 second with a temporal resolution of 1 millisecond. So that means you have 1,000 data samples. And for this 1,000 data samples, you need to store a copy of the network dynamics for every sample until you get the final error, and you can finally backpropagate the gradients through the whole network dynamics. So this is a process that is known as unrolling in time, and that leads actually to very big effective depth for the network. So for example, here that would lead in the example that I just showed about 1,000 layers. And to give you an order of magnitude, current integrated circuits that can perform on-chip training are limited to about 3 layers. So that's really leading to intractable memory and latency requirements. And this is why no end-to-end on-chip solution has been proposed to date to deal with temporal data. So this is really the key challenge that we'll look at, on-chip learning over long time scales while keeping a fine-grained temporal resolution. So now we come to a hint. Obviously, the brain doesn't do backprop through time, and hopefully Bojan just before has nicely introduced this problem before. So we have that the standard for backprop through time is a backward mode training, where you need to keep a copy of all time steps. There are also forward mode training algorithms. So Bojan has presented forward propagation through time, and indeed now in this talk I'm going to talk about EPROP that was also addressed in the Q&A. So EPROP, or eligibility propagation, was proposed in this paper, and the key idea of EPROP is that it approximates the backprop through time gradients as the product of two terms. One is an error-based learning signal that is available locally in time. So that is the main assumption that is done by EPROP, is that this error-based learning signal is available locally in time, and this is what is shown here. And the second term is what is called an eligibility trace, a synaptic eligibility trace, that basically represents the importance of every single synapse onto the network output. And what is nice is that these eligibility traces are computed exclusively forward in time, and they are not error-based. So this is really a trace of activity that we keep over time. And what is the super nice property is that we only need to store the current time step. We can perform this learning online, and we do not need to wait for the final error and to buffer all the network states before we can apply the updates. So going from one to the other, we can actually see that the biological plausibility is increasing, especially because eligibility traces are supported by biological evidence. Space and time locality go up, and we have seen in the STDP example that space and time locality are everything for both, of course, neuroscience and hardware efficiency. And therefore, this completely slashes the on-chip memory requirements, because you only need to keep in mind the current time step to perform this learning. The challenge, though, is that EPROP is still not fully amenable to a full end-to-end on-chip hardware implementation due to a few remaining challenges, and this is what we'll focus on in the remaining part of the talk. But before that, let's just quickly summarize what is the network model that we'll select. So here we take a recurrent neural network of spiking neurons. So here comes another question: why spikes? Is because EPROP was proposed as a bioplausible alternative to a backprop through time. But so for now, we'll select spikes for the sake of bioplausibility, but we'll see that from an engineering point of view, there are some nice properties that spikes have for which we want to select them. But I'll come back to that shortly. So for now, we need a spiking neuron model in the recurrent layer, for example, the leaky integrated fire neuron that has been covered quite extensively already. So I'm just denoting here this alpha term is the leakage decay factor. Here the theta is firing threshold. As soon as you reach it, you fire a spike and you reset. What is the output neuron model is exactly the same, except that we remove the firing mechanism and the reset, so it's just a leaky integrator. And why no spikes at the output is just to avoid ill-defined spike-based error definitions at the output. Next, we need a task to monitor all algorithmic requirements. And so a nice task is this delay supervision navigation task, also sometimes called queue accumulation. This is a typical task of neuroscience. So you have a rodent moving along a corridor. It sees cues on its left and right, so here represented by small squares. In the first phase, it will see the cues. So here you see, for example, there are 4 cues on the left of the rodent and 3 cues on the right. Then it will traverse a cue-less phase, and that it has to decide to turn left or right, depending on the direction in which it has seen the most cues. So in this case, the good solution is that the rodent should turn left. So it really has to maintain a working memory of what happened in the past in order to make the right decision. So this is taking place with short-term dynamics over second long time scale. So this is exactly the use case that we are looking at. And interestingly, this is a complex task, because if you take vanilla backprop through time with a standard leaky integrated fire neuron with a bioplausible leakage time constant of 20 milliseconds, you have that this network is completely unable to learn to solve the task. So even with vanilla backprop through time. But interestingly, if you just use a slightly more complex neuron model, such as the adaptive leaky integrated fire neuron, where you have threshold adaptation, then suddenly the network is able to learn to pick up the dynamics and learn to solve the task. So why is it so? It is because for the standard leaky integrated fire neuron, you only have a short time constant of about 20 milliseconds of leakage in biology. While for the adaptive leaky integrated fire neuron, which is arguably more bioplausible, it embeds threshold adaptation over hundreds of milliseconds. And this is indeed sufficient to induce long temporal dependencies in the network dynamics and to learn to solve the task with backward through time. But the price to pay is that I told you eligibility traces are dependent on the selected neuron model. And eligibility traces are really simple for the standard leaky integrated fire neuron. It's just a simple activity low-pass filtering, nothing more to do. But for the adaptive leaky integrated fire neuron, then it becomes completely intractable. And this is already difficult enough for a GPU, so forget about dedicated hardware about this. This leads to complex per synapse multi-timescale filtering. So we really do not want to do that. So that's the first challenge that we need to solve for EPROP in order to make that amenable to an on-chip implementation. What neuron model should we select? And here, actually, it's time to depart from neuroscience and go to a more engineering approach. We will take a non-bioplausible neuron model. So we'll just take the leaky integrated fire neuron model, but now we'll make the leakage, the membrane leakage time constant flexible from milliseconds to seconds. So going with a membrane potential leakage of up to seconds is not bioplausible, but we can get the best of both worlds. So we can get this flexibility in the time constant, you can have long temporal dynamics, and you can keep very simple to compute eligibility traces, which are just a simple activity low-pass filtering. So this is the first step that we do. Second step, we can now write the EPROP equations for the leaky integrated fire neuron. So we write here the equations for the output weights, recurrent weights, and input weights are as defined here. So I told you before, the EPROP is about the product of a learning signal that is error-based and an eligibility trace. So the learning signals, here you see the error definition. And for the recurrent input weights, you need a projection from the output readout matrix. But indeed, the learning signals are just an error-based term. First problem that we can see is this sum term here. It requires what we call a dedicated gradient memory. What it does is that you actually need to sum all the updates that are computed by EPROP over all time steps before applying them. So in hardware, that's difficult because you need a dedicated memory to store all these updates before you can apply them, but that's also not bioplausible. Your brain does not store all the updates in a specific part and then carry out the updates at once as a second phase. So you again have this duality between neuroscience and hardware. So what we can do is to just cut this term and perform per time step updates. So we perform the updates at every time step, and that will work just fine as long as the learning rate is small enough. So now we got rid of the first problem. Now let's look at what is inside eligibility traces. You have actually three things. The first one is what I mentioned, the presynaptic activity low-pass filtering term. And you see that the filtering term is depending on the leakage of the neuron. Hence why if you get a long leakage, you get a long timescale eligibility trace. The second term is a postsynaptic straight-through estimator, also called sometimes surrogate gradient, for the activation function. So this is just the smoothened spiking activation function derivative. And the third thing is that actually the problem with EPROP is that you have a temporal coupling of these pre- and postsynaptic terms. And this is actually very expensive to compute because you need to remember the product of these terms over time. So what we can show is that compared to the assumptions already done in the original EPROP algorithm, this temporal coupling term can be safely neglected. So what actually we end up with the modified EPROP equation that we propose, we have a learning signal, we have the straight-through estimator term, so this surrogate gradient that is a postsynaptic term, and you have this activity low-pass filtering on the presynaptic side. So what you can see is that now we achieve this full space and time locality that we have seen before for STDP is really key for both hardware efficiency and bioplausibility. And that allows us to completely decouple the pre and the postsynaptic terms. And why is it nice? Is that storage and computation-wise, now you can, everything scales with the number of neurons and not anymore with the number of synapses. And therefore you can really cut the memory overhead of this algorithm. Third thing that we need to do, and I will, for the sake of time, skip quickly on this, we need to quantize the weight resolution to minimize the hardware requirements. And then we show that 8 bits is a sweet spot if you combine that with stochastic weight updates. So that's just for your information. Now we can look at the results. Here in black, you have your or modified EPROP algorithm with a 2-second leakage time constant of this leaf neuron that we propose. So this is actually issued from chip measurements. First thing that we can do, that we can see, is that it's competitive with the backward through time trained with network of ALIF neurons, which was our baseline. The second thing is that we can do this with only about 1% memory overhead compared to the inference-only network. So you take your inference-only model, you add 1% memory overhead, and you are able to learn over second-long timescales. So this is the main takeaway, but now, in case you lost a little bit track of it, let's go back to the big picture. I have mentioned that neuromorphic intelligence, you should start from the engineering approach and should feed it by insight from neuroscience. So we have taken as a starting point backward through time. The main challenges that we have encountered is that it's not tractable hardware-wise, and it's not bio-plausible. So let's look into neuroscience. Neuroscience tells us, okay, eligibility trace might be a thing. And indeed, it leads to the EPROP algorithm that solves these two issues. But EPROP is still not fully amenable to a hardware-efficient implementation, and is not by default able to learn over long timescales. So you need to combine that with a powerful neural model. And so what neuroscience tells us here is that you need to have threshold adaptation, but it's still not hardware efficient. So we leave neuroscience and go to an engineering approach. We take a configurable leaky integrated fire neuron. And this, combined with a simplification of EPROP for space and time locality, we end up with this simplified EPROP algorithm. So this is the schematic correspondence of this approach that we propose. So now with this simplified EPROP algorithm, we can implement that on a chip. So here is a cute, cheap microphotograph where everything has been implemented in less than 0.5 millimeter squared of silicon. So this is a tiny chip. And so indeed, you have 0.5 millimeter squared of silicon. And what I would like you to remember is that there is no external memory. So everything happens inside the chip. And so here is the kind of high-level overview. You have here the chip itself, and it communicates with spikes with any kind of sensor. So it can be a spiking neuromorphic retina, it can be a spiking cochlea. The chip doesn't need to know anything about the sensor. As long as it talks with spike, the chip will figure out how to learn with these spikes. And so I'm coming back to something that I have mentioned earlier. Why should we use spikes? So oftentimes spikes are selected because they are event-driven. They allow for event-driven and sparsity-aware computation. But they also allow, and that's what we show here, for sensor-agnostic raw data processing. And if you combine that with a learning algorithm that is agnostic to the spike code, as EPROP is, you end up with a task-agnostic processing and learning chip. So everything is open source, actually. If you would like to prototype the chip yourself using an FPGA, you can. But in order to demonstrate this task-agnostic processing and learning, we need different kinds of benchmarks. For example, we can demonstrate that with a vision dataset, such as the IBM DVS gestures datasets. For example, you have 10 classes of rolling arms, clapping hands, rotating left and right arms, air drums, and air guitar. And this unfolds over 6 seconds with about a 5 millisecond temporal resolution, as we have selected here. You can select an audition dataset to do some keyword spotting, for example. And here you can take the spiking Heidelberg digits dataset. So what we show here is that every digit is about half a second in length. And here on the y-axis, you have the different channels, and with the lower channels representing lower frequencies. So for example, this is a 6, and you see the NX represent the higher order frequencies, and this is a 7. A third dataset that we can choose, this one you are already familiar with now, is the delayed supervision queue accumulation task. That is a proxy for the navigation use case. And we have that for all of these tasks, from scratch and without external memory, our chip has been able to learn to perform them with a quite reasonable accuracy. So 87% for this vision task, 91% for this keyword spotting task, and above 96% for this navigation task. And what you have to see is that for all of these tasks, for real-time learning, you need less than 50 microwatts to perform this real-time learning. So to give an order of magnitude, 1 milliwatt is the kind of low power for your phone. So if you go to the microwatt range, this starts becoming adequate to perform user adaptation in wearables, for example, where the battery size is really critical. So in terms of the key messages that you should remember, you have that following this nice blending of AI algorithm, neuroscience, and hardware, we have demonstrated the Reckon chip, which is able to perform end-to-end on-chip learning over second-long timescales, while keeping a millisecond temporal resolution, which is a yet unsolved engineering challenge. The second thing is that we provide a low-cost solution thanks to this, just because we require less than 1% memory overhead, so less than 0.5 millimeter squared in silicon area, and less than 50 microwatts for training at 0.5 volts. Third thing is that we can demonstrate task-agnostic learning, which opens new doors for user customization and even full chip repurposing at the edge. So that outlines an exciting future for neuromorphic intelligence. So that's a good opportunity to thank my former mentors and colleagues. And because now I'm actually working hard on forming my own team in TU Delft. In case you would like to explore also the future of neuromorphic intelligence, you're very much welcome to drop me an email, because I'll be looking for some new team members very soon. And that's it for me. You have here a few references, the links to all open source repositories, as well as the ways to contact me. So thank you for your attention.